Right, the wonderful world of oscillations, and in particular this topic focuses on simple harmonic motion. The key thing to remember about simple harmonic motion is this little relationship, and the missing symbol of course is the proportionality symbol that goes in the box there. What it says is that the acceleration A is directly proportional but in the opposite direction, hence the minus sign, to the displacement y. That is the cornerstone equation for simple harmonic motion. The other important thing is that this develops very quickly into the equation where the constant of proportionality is the angular frequency squared. Keeping the negative sign, we get the equation A, the acceleration, equals minus omega squared y. And that applies to all simple harmonic motion questions. The key equation to remember. Cannot stress that enough. So a couple of examples here. Starting with an ocean swell which moves up and down in simple harmonic motion. The amplitude is given as 3 meters, and we've given a frequency of 1/4 of a hertz. Right, A, what is the period of the simple harmonic motion? Of course, capital T, the period, is the inverse of the frequency, so simply taking 1 over 0.25, you'll calculate 4 seconds for the period. The angular frequency B of this particular motion, omega, is the angular frequency symbol, 2 pi over T, or 2 pi F you could use. Anyway, both ways give you half a pi. Half of pi is 1.57 radians per second. The 3 figures. Right, C, what is the maximum vertical velocity of the water, and where does it occur? Of course, it always occurs. We should know from the theory by now, hopefully, that it always occurs at the fixed point or the midpoint, or perhaps called the equilibrium position of the motion. And so for an ocean swell, that would be where there's flat water, yes, the equilibrium position. So that's the position. The actual value Vmax is found from omega A. So we just plug those values, 1.57 multiplied by 3, that gives you 4.71 meters per second. Okay, part D, what is the maximum acceleration of the water and where does it occur? So Amax is related to angular frequency, of course, and the amplitude A. This comes from the initial equation, acceleration equals minus omega squared y, and when y is maximum, so is the acceleration, I should say. So, plugging the values in, we get negative 1.57 squared times 3, and that gives us 7.40 meters per second squared. That's the maximum acceleration. E. Write equations for the 3 quantities, displacement, velocity, and acceleration. So, starting with displacement y, we can put in A sine omega t as a general equation, but since we have those values, or some of them, we have the amplitude 3, and we also have the angular frequency omega as 1.57. We don't have t, of course, that's the only general thing left. So there's the equation for displacement. And we could calculate the displacement at any particular time t just using this equation. Next we have the velocity equation. Velocity is omega a cosine omega t. Once again, omega a is the maximum velocity, which we've already calculated, to be 4.71. So putting that in instead, times the cosine of omega t, 1.57 t. And lastly, the acceleration equation. We have the maximum acceleration 7.40. We just calculated that. Whoops, I forgot the negative sign. Put it there. Sine of omega t, 1.57 t. And there are the three equations. Now we can use them to calculate each of those three quantities: displacement, velocity, and acceleration of the water after 1.2 seconds. And since the period of oscillation is 4 seconds, you'll notice 1.2 seconds is basically just after a quarter of a cycle of the ocean swell, which is probably just when it's coming down from its highest value, and it's on its way back down through the equilibrium position. We're not quite there, of course, it's just come off the peak and on its way down. So we're expecting to have a negative velocity value and a displacement value just under 3 meters. So if we plug in the value for 1.2 into this equation, we get 1.57 times 1.2, take the sine of that, and then multiply by 3. Let's see, what do we get? 2.85 meters. And as we expected, that's just under 3 meters, so it's just come off the maximum displacement and it's on its way back down. Now plugging in the velocity, time 1.2 times 1.57, taking the cosine of that and multiplying by 4.71, we should get a negative number. And we do. That works out to be negative 1.45 meters per second. Now that's nowhere near the maximum value, which is 4.71, and that's to be expected because it's nowhere near the midpoint yet. It's only, what, 15 centimeters away from the maximum displacement, where the velocity is momentarily zero, of course. So that checks out. The last one, acceleration at 1.2 seconds, just plugging that in. And we expect a negative sign again here. Do we? Yes, we do. Negative 0.703 meters per second squared. Now that negative sign is telling us that it's in the opposite direction to the displacement. And since the displacement is a positive number, 2.85, we do get a negative acceleration value. That means it's directed in the opposite direction from the displacement. So in this case, it's back towards the equilibrium position as always. That checks out. But make sure you can actually get these values using your calculator in radians, of course, when you're calculating the sine, the cosine of omega t. Okay, number 2, from the previous example, find the velocity of the water when it is displaced 2 meters from the equilibrium point. Now we could do this the long way, but the short way is to recall a very useful equation that relates velocity to any position y, which is plus or minus the angular frequency omega multiplied by the square root of the difference of the amplitude squared and the displacement squared. So that's the key equation to remember. It relates the velocity straight to a particular displacement y, where we are given or know, or perhaps have calculated already, the angular frequency and the amplitude of the motion. Which is the case, of course, for this example. So we just plug the values in carefully. 1.57 for the angular frequency. Then we're taking the square root of 9 minus 4, that's 5. So square root of 5 times 1.57, you should get 3.51 meters per second. Now, just thinking about the answer, is it a sensible figure? It's less than the maximum velocity value, which is 4.71, and considering that we're 2 meters away from the equilibrium position, that makes sense, and that kind of it doesn't say whether it's displaced upwards or downwards, so we're going to have to just put plus or minus in there as well. Okay, number 3. A 200 gram mass is attached to a spring with a force constant of 10 newtons per meter. It is then displaced so that it undergoes simple harmonic motion with amplitude of 15 centimeters. What is the period of oscillation of the mass? Now, we could calculate this the long way if we wanted to, by considering the force to give us the extension of 15 centimeters. We could calculate the force and then calculate the acceleration or the maximum acceleration and so on. Relate that to the amplitude or the displacement and find omega, and then find the period. But that would be quite a long way of doing things. The short way is to remember the equation for the period of a spring. So that's capital T equals 2 pi times the square root of mass m over the spring constant k. Now if you plug in the values, you've got 0.2 kilograms for the mass, must use SI units, and you've got 10 newtons per meter, which is SI units already, for the spring constant k. So 0.2 divided by 10, taking the square root of that and multiplying it by 2 pi gives you 0.89 seconds to two significant figures.